So this is my short introduction to the seminar, and now I'd like to, I have a great pleasure to present our speaker today. Leo Alves, he's from UFF, stands for what? University?
Fluminense Federal University.
Brazil. Yeah, from University of UFF University from Brazil. He received his master and PhD degrees from UCLA, and he's working on various marching schemes that allow to reach steady-state solutions when it is possible, and he tries to address all kinds of challenges that relate to marching schemes in steady-state CFD solvers. And with this, please, Leo, I will not take any more time. And thank you for visiting us and for presenting. So that's an exciting day for everybody.
Yeah, thank you for the invitation. It's a pleasure to be here. And I'm going to be talking to you about something that has been in the works in our group for the past 4 or so years. My background is on stability analysis and DNS as well, and but the focus of this work is going to be essentially just DNS for steady states, and I'm not going to be talking about the stability that we do with these steady states. And And so this work has been done mostly in this project by these 3 students. Maybe I can use the mouse. Yeah, Ricardo, Mateus, and Rodrigo. Ricardo is in industry making money now. He left us, but he helps out a lot. It's quite good. Mateus is currently, he did his undergrad and master's with me. He's currently with Lianduan at Ohio State with his PhD. And Rodrigo decided the pandemic was too much, and they moved, his family and him moved to Portugal. So they're not even in Brazil anymore. So we have a new student, Juan. There's a different Mateus also. There are a couple more students. Juan is the main one also working on this project. And we have Romulo, who's here at NIA for the past few months, also been working on this. I want to mention also this has been done in collaboration with Vasilis. The first part of this talk, there's going to be a lot of interaction with Vasilis. And the last part is when the interaction with Pedro starts. So this has been done mostly with funding from AFOSR. They have a Southern office for South America, and we get grants through that. There's also been grants from CAPES. CAPES and SINPQ are federal funding agencies in Brazil. CAPES does mostly like fellowships for graduate programs, and SINPQ actually funds like research grants. FAPERJ is the same thing, but is a funding agency from the state of Rio. So they also help out throughout the years, and they're all funding grants related to this steady state stuff that we do. Of course, we have to say that. So the talk is going to be divided this way, a brief introduction to separate like what we've called the 3 major challenges when doing steady states, right? And I look at it, like I said in the beginning, my background in stability, so I look at everything from a stability point of view, both physical stability and numerical stability as well. So I'm going to use those concepts to separate these 3 different groups that I mentioned here when trying to tackle to get steady states for these 3 different cases, because they present different challenges. So for now, it's just a brief introduction on this separation. This is just fundamental stuff, but to understand that the reason why we do these steady states is for stability analysis. And we need to be careful with that. If you have just any random unsteady system, your steady state is defined this way. This is straightforward, but few people actually check this when they are running their steady states. If you look at papers, people don't show residual convergence in time, and they don't show these things. So this is crucial to know that you're at your correct steady states. Usually people just look at increment of the solution in time, but that's not enough. We're going to talk about that later. And the key thing to understand is that we are doing this for stability. So if you do stability based on a random base flow, and you plug that into your governing equations up here, what you get is actually something like this. You have a Jacobian matrix that is evaluated at that base flow that is not really a solution of your governing equation. And you actually have source terms as well that look like this. So this type of stuff presents you with criteria that you need to satisfy in order to make sure that your base flow is accurate enough for instability analysis. So the last one tells you that whatever residue that you get from your base flow has to be smaller than whatever is the amplitude of the disturbances that you expect to contaminate it, and to the order square. And this one, there's some math that you need to do behind it, but it actually tells you that the difference between your base flow and a true steady state solution of your equations also need to be smaller than that order. So if you do that, then whatever approximate base flow that you're using should be good enough for stability analysis. So these are important concepts to have. And so how do you get there? How do you get to this? How do you get with your base flow solver? How do you get close enough to steady state to satisfy these things? So that's the general goal of this project. So when you do that, then you are truly in your steady state and you are doing this, which is the proper stability linear stability analysis.
One question. So do you assume that the steady state solution is unique?
No, I'm just getting a steady state solution. And there's a test case here. We do some test case in which there are multiple possible steady states, and you can converge to different ones. And I'll get there, you see. But I don't assume anything. I'm going to give you a steady state that is a solution of the governing equations, right? If there are more, you need to find them. And because with marching schemes, it's very similar to iterative schemes. Depending on your initial guesses and the radius of convergence, you might go to different places if there are multiple steady states. But so this is just a basic stability map that probably all of you are used to for the explicit Euler scheme in here and the implicit Euler scheme in here. This light blue region is the region of numerical stability. And I just present you with the gain with the eigenvalues defined in this way. So on the horizontal axis, what you have is the physical temporal growth rate of whatever modes are in your physics, right? If that guy is positive, then your flow is, and you are on this right-hand side here, your flow is physically unstable from a linear and time asymptotic sense. If this guy is negative, then you are physically stable in the same sense. And this vertical axis here is the imaginary part of that gives you the frequency, the oscillation frequency. So if you have a frequency, your mode is here. If you have so this is a traveling disturbance, and this would be like a stationary disturbance, right? So this is how you interpret your thing. So this presents you with the three branches that we need to be careful with, right? If you have like a physically stable flows, which are the green ones, then that's why, for instance, when you're running like an explicit marching scheme, you need to make your time step small enough so those physically stable modes, they can go into the numerically stable region of your scheme so you can get convergence to steady state, right? If you have physically unstable modes, there's nothing you can do with explicit schemes. They're going to still be physically unstable, numerically unstable. And this also makes it clear why the implicit Euler scheme is such a popular scheme for steady state generation, because you can get the physically unstable modes in here to still be numerically stable, so that you can converge to a steady state even when there's physical instability in there. And whereas like the stable part is always stable. And these modes are modes that I'm calling physically unstable with frequency, a complex frequency different than zero. What that means is that there is either lambda is not zero, right? There's a real and imaginary part, temporal growth rate and frequency. Either one of the two must be different than zero. If you have that, then that's to what most steady state solvers were designed for, and they work for those conditions. And I also mentioned here the thing in red, which is the troublesome part, which is actually this. The most troublesome part is this dot in the middle, which is I call the lambda zero modes. And because they are stationary, so the imaginary part of that lambda is zero, and they are on a time asymptotic sense, the temporal growth rate is also zero, right? And so that mode is really troublesome. And physically speaking, what is that? That manifests itself as like a convective instability to stationary disturbances, right? So that's what you see. And that's the last part of the talk. And that type of mode, there's no current steady state solver in the literature that can solve that. And I'm going to talk about it in the end, is the biggest challenge that we have been trying to face. Yeah, I didn't mention this plot on the bottom, but you guys understand what is this. So the first part, we're going to talk about is physically stable flows, so that first we looked into this because then we can focus on the spatial discretization that we need in order to be able to get the correct steady states. And then we go on to deal with what do we do when we are marching these things in time when they're unstable, right? Basically, there are two problems that we tackled with this, like a flow around the cylinder and the compression ramp. The flow around the cylinder, people usually use it to test the spatial discretization for carbuncle to see if you're getting properly symmetric base flows. And there's a lot of low order and high order simulations. But what is interesting is that all the steady states, all the stability analysis that I found in the literature for this problem usually use like low order accurate steady states for the stability analysis. So it was interesting to see what we can find out with more than that. Which are the last bottom two topics. And also a lot of the stuff focused on the dynamics downstream of the cylinder. We wanted to see on a supersonic sense what happens to the shock. What are the kind of stabilities related to the shock? So this is, this is the name of our code. They call it like 3D4S. We're not very good at naming things, but this is the name of it. And we have like a low order and a high order version, right? The high order one, this is just explicit Euler because it's physically stable, so it doesn't matter. So we are doing the characteristic-wise Lax-Friedrichs flux vector splitting with a fifth order WENO and fourth order conservative difference for viscous fluxes. And we have some analytical grids that we use. And we can show that for this problem, we do get residue convergence in time of several orders of magnitude. And this is shown here for Reynolds number 1,000, Reynolds number 10,000. We do get a proper residue convergence in time. If you look at profiles, I think this is at a 30-degree angle, you can see that we do get some spatial convergence of those profiles. But at the higher Reynolds numbers, we do see some wiggles when the mesh is poor. And if we plot for instance, the isocontours here of velocity, they do look fine. They do look nice. There doesn't seem to be anything wrong with them. But then we go on and we look into the disturbance behavior, and we can actually see striations. I always keep losing my mouse. I do see striations coming off of the 10,000 Reynolds numbers, right? And this mesh is an analytical mesh. This is not aligned with the grid. And so this is the type of problem that we are trying to deal with it now, because we still think this is some sort of manifestation of carbuncle. And the next step that we're trying to do is to align the mesh with the shock to see if we can get rid of that. Because if you go through the literature, you're going to find out that people think that carbuncle is usually associated with flux difference schemes, and flux vector schemes don't have that. And as I was talking to Pedro the other day, if you go to a high enough Reynolds number, this thing shows up. So even with flux vector splitting, and we know characteristic-wise everything that you think of, this is still some structures coming off of the shock. These actually appear not only in the disturbances, but if you zoom into the base flow, you can see them there too. So this is affecting your solution, and we need to get rid of that before we can use those as steady states for stability analysis, right? And so we do think this is carbuncle. This is just the things that I'm just saying right now. Yeah. So we are doing the shock alignment now to see if we can, that is enough, because again, in the literature, they say that alignment of the shock is essential to remove these things. So we're trying to test that right now to see if we can get rid of that. This is another interesting thing that I put here as future work, but we implemented it recently. There's been a new WENO scheme developed, 2018 by Zhu and Shu, which is to deal with most WENO, the classical one, the WENO Z, WENO mapped, and all of them, they suffer from post-shock oscillations in unsteady simulations, right? Which prevents the residue from converging in time. And they developed this new WENO that was designed for steady state calculations that they don't suffer from that, and you do get residue convergence. And that was already implemented. I'm not going to talk about this. Yeah, we can move on. Because we did some stability analysis for this problem, and we found out transient growth in the bow shock. And we are trying to do some unsteady simulations to verify if that transient growth is indeed there or not. But I don't need to go too much into this. And so we are able to get higher order accurate steady states for this problem, but only for low Reynolds numbers. For high Reynolds number, there's still more that we can do. We do need to do more grid line meshes to get there. And for this particular case, we didn't need to do this new WENO for steady states. We didn't do it yet. We're going to try to test that to see if we can get rid of the striations as well. But we did use it in the next test case that I'm going to talk to you about, which is the 2D flow of a compression ramp, right? And so this problem was really posed as a challenge to us at Vasilis at the time. He was trying to do a stability analysis of this, and he couldn't converge a base flow. He was trying to ask people to give one to him, and he was trying to use open foam, and he couldn't converge the base flow at all. So he asked us to look into this, and it gave us a lot more trouble than we initially expected. But so we wanted to understand what was going on. So first we tried the low order version of our code, which is the standard like TVD type stuff. We have a bunch of flux limiters. So here is a super B, second order conservative central difference schemes for the viscous fluxes. Again, this is a physically stable problem, so we do explicit march into steady states. And in here, we are running very low Reynolds numbers. And the story here is that when you go from Reynolds numbers 2,000 based on the plate length to 5,000 to 10,000, you see that the residue convergence in time no longer happens, right? It does look like you have a converged spatial profiles. This is the spatial profiles along vertically along the wall at the corner. And they do seem converged, but the residue doesn't converge in time, right? And so we start probing the simulation at different positions, and we do see during the process, we do see these oscillations, right? They start to appear upstream of the separation region, and they get really strong in the separation region, but they sort of decrease in magnitude as you get to the corner and to the reattachment region as well. But it looks like they're coming up even before separation, right? So there's some issue there that is generating some unsteadiness in the code that doesn't allow the residue to converge. And that's problematic, right? You're exciting, you have temporal excitation in your simulation, right? And I remember Vasilis mentioned in some NATO meeting, people talking about, how is it, a mean laminar solution. And that's what people resort to, right? You have this unsteadiness, so you take means of it, but you're not supposed to have a mean laminar solution, right? It's supposed to have a true steady state. So people try to do all kinds of things to get around that, but we are trying to understand why. And so we decided to do the same thing, and those were for like isothermal wall conditions, and we did the same for adiabatic wall conditions as well. And this is a comparison between the low order version of our code and we do see a same problem, right? We switch the boundary conditions to adiabatic, the residue doesn't decay. And then we probe the code this is in the compression fan at the separation point, at the corner, and around the reattachment compression fan as well. And we can see that there are like unsteadiness in there that doesn't allow the residue to converge. And then we switch to this WENO scheme designed for steady state simulations, and then voila, we no longer have any problems with that. If we can get a mesh refined enough, you get the several orders of magnitude convergence in time, and we eliminate the unsteadiness. And we could do that here because of this new WENO for steady state that is designed to avoid this post-shock or shock and compression fan related oscillations in the spatial discretization, right? So this was crucial for us to be able to get steady states, even when it's supposed to be like a physically stable problem, right? So this is the issue with making sure to look at that first to make sure that our spatial discretization is nice enough to handle these things before we can go to unstable problems. Yeah.
How do you know that these problems are physically stable? I mean, the WENO scheme could have spatial numerical dissipation that would overwhelm any. It's a question.
Yeah, so he's asking me, how do I know that this problem is stable? And yeah, this is the part of the talk that I didn't prepare any slides for, because, but we did a lot of stability analysis for this. If you want to look into this, I think I presented some of this stuff in ICAS. But we are we're finishing the paper right now. But all the stability results for this are there. So just to summarize, if you take I actually have some stuff for this, but from the DNS. But if you look at the 2D flow, it is modally stable always, right? So the instability here happens for three-dimensional disturbances. Two-dimensional ones are always stable in a time asymptotic sense, right? And they do get closer to marginal stability as the Reynolds number increases, but they are always stable. So we see that in our simulations, we can use the residuals method to extract the disturbances, and we see that. But when we do stability analysis based on these steady states, we see the same thing. That's how I can tell you that it is, because we've done the work. Although I'm not showing it here because we are focusing just on the steady state stuff. So you can see, there's a plot further down, and you see that. So you can show here, we can get these like several orders of magnitude decay for the residue for Reynolds numbers going from 2,000 to 200. And we did actually 300,000 Reynolds numbers, right? And most of the studies in the literature, they deal with Reynolds numbers that are of this order of magnitude and higher, like 400,000, 500,000. They also deal with higher Mach angles and higher ramp angles and higher Mach numbers. Our concern here was actually to look at lower Reynolds numbers because we are interested in the onset of instability, like when this problem first becomes unstable. And you can see that we do get properly grid converged base flows. This example here is for the Reynolds number 200,000, which is pertinent because the critical Reynolds number is around that value. And you can see that our profiles are properly converged. You can see the properly resolved leading edge shock, the compression fan, the separation compression fan and shock, reattachment compression fan and shock, and the recirculation region. Everything is properly resolved here. And we can get through residue convergence in time at all these Reynolds numbers, right? You're seeing here 10 orders of magnitude of decay in the residue. And we took this to measure these formulas, didn't come out, right? I'm sorry about some mishaps with the presentation because it was done in Mac and it's been read in PowerPoint and Windows, so there's always some issues there. That's beyond my expertise to understand why. But so we also measured incipient separation. So at which point that recirculation region first appears, we're measuring the wall shear stress. With all these steady states, we can try to estimate that. We also did some calculations, not me, but Nick, which is one of Vasilis' students, did some triple deck calculations to compare with our DNS. And there's some validation here of a triple deck from the original study from Cassell and the current calculations showing that we are doing an okay job. And when we compare the DNS, which is the black dashed line, with our with the triple deck theory of our DNS, we can see that the solutions within the recirculation region, they agree pretty well. There's some disagreement further downstream of that and upstream of that, but in the recirculation region, that it's pretty good. And this is the question that you're asking me before. We can, in our 2D simulations, we can use this method to extract like the decay rates of the disturbances, right? So when we're converging to steady state, usually the thing that convergence is usually dictated by the least stable mode, the one that takes the longer to decay. And so that's what survives after some time. So if you look at asymptotically, if you look at that and you measure the decay rate, you can then compare that with stability analysis. I have one point here that we did for comparison. So for the case of 50,000 Reynolds number, the decay rate obtained from the linear stability analysis using our steady state gives me a value of, the mouse keeps disappearing. It gives me a value of this red circle that you're seeing here. And the blue dots are the decay rates measured from the DNS itself. So they match pretty well. And that's why I was telling you that this is the 2D base flow is always modally stable. It approaches marginal stability as the Reynolds number increases, but at least for this range is always stable. That's why I can say that this is a physically stable case. Again, on a modal sense, like time asymptotic, very large times, and linear sense. And Another interesting point to make here, you can also extract from the DNS what the disturbance shape looks like. And I think a point to highlight here is that if you look at the disturbances, most of the structure is concentrated in the shear layer region, but you do have structures in the compression fan and the shock also. So this is quite interesting, and it's also pertinent to the work that Camille and Romulo are doing with Pedro, which is try to design stability solvers that can handle the shock discontinuities, because in some cases the disturbances have structures in the shock, so you need to be able to capture that, and we are showing this here. This is U and V, you can even see it better in the V profile. Both the compression fan and shock at the separation and reattachment, you have structures from the perturbation there. So this is really important to highlight. So what we found out is, so there's a lot of flickering because of when you do the low order stuff with TVD, flux limiters are a pain, they flicker a lot, and the main cause of these oscillations, and that prevents convergence in these things. And when you use WENO, if this is steady WENO, we can get rid of all these oscillations, and we can converge our residue in time and remove this temporal content in the steady states, right? Right now we are trying to run some 3D simulations to verify the temporal growth rates and the 3D disturbances that were found to be unstable after the onset of instability. There's a lot of stability analysis done for this problem, but I'm not showing any of it here. And we're also trying to generate the onset of instability in this problem is also stationary. It's a three-dimensional disturbance, but it's also stationary, which suggests that there could be another 3D steady state for this problem. And we are trying to see if we can get there and leave that as a present for Pedro to play with later. So to do like secondary stability analysis, right? We have stationary 3D disturbances that grow, contaminate, distort the mean flow, then you can get that new steady state and do stability analysis on it as well. And you're gonna ask something?
Yeah, so like many production codes, I know they freeze the flux limiter beyond a point because of that issue.
Yeah, what I've seen people do a lot. So he was asking that. Yeah, so he was asking that, he was saying that a lot of people freeze the flux limiter to prevent these oscillations. What I've seen people do a lot too is try to get to as close as you can to the steady state to find out where the shocks and the high gradients are. And then you turn on, you have a manual flux limiter that you turn on exactly where you want, and you leave it there, and then you rerun the simulation with frozen with that state. I've seen that done too. But yeah, you have to do all kinds of gimmicks to try to get that. But we found that this WENO, this steady state WENO, is fairly robust. We don't need to do anything. It runs really nice. So now we are going to go to the second case, which are physically unstable flows where the complex frequency from that numerical stability analysis is non-zero, right? So it can be stationary disturbances, but they must grow in time. Or they are oscillatory disturbances that are like marginal in time or grow in time as well. Something has to be non-zero in that lambda. So this is the typical steady states that people use. We have the Newton method. This is very good quadratic convergence rates, but it's very sensitive to initial guesses. And we also need to put a Jacobian in. Implicit Euler is very popular. It's a lot less sensitive to these initial conditions. It's L stable, but also needs a Jacobian. So if you're a fan of explicit marching, people usually run away from that. So in order to avoid using these things and try to design things that work with this explicit scheme that don't need this Jacobian matrix, a couple of methods that I highlight here that have been developed not that long ago. Selective frequency damping. You can attach it as a black box to an explicit marching scheme. It will damp and get to steady state, but it only works for self-excited, single frequency self-excited global instabilities, right? So you can filter out that disturbance as you converge to steady state. And BoostConv, oh, there's a T missing here, was recently developed. The selective frequency damping is from the Dan Hennison's group at KTH. BoostConv is from Lucchini's group in Italy. It also works as a black box. You can attach it to an explicit marching scheme. But a lot of people have been using it, and there is some difficulty in finding the correct control parameters to allow convergence, right? So it's not that easy to use. So we took a different approach with this, right? The way we look at it, we're not going to try to go for explicit marching schemes. Let's look at the Newton and implicit Euler schemes and see what happens to them. And one of the major problems that we found when using, because we use implicit Euler scheme a lot in the past, is that there is always some issue that restricts the maximum time step that you can use, right? Simulations of the cone, usually you just simulate the nose first because you can very low CFL numbers that you can impose there, and then you go on to the rest of the cone. So usually what happens, it can be stiffness, it can be nonlinear effects, a lot of things that can restrict the maximum time step that you can do, the maximum CFL that you can do. So what does that do? You go back to the stability map of the implicit Euler scheme again, and what happens is that if the maximum CFL that you can use is, on the best case scenario, what you will do is to prevent you from going to small enough gains, and that's why your convergence is low, because the convergence to steady state depends on how small the linear gain of your method is, right? If you can do infinite time step, the implicit Euler scheme becomes the Newton method. But if you're restricted, then the gain will not be so low, and then the convergence to steady state will be slow. That's the best case scenario. The worst case scenario is that your time step is not going to be enough to place these physically unstable modes outside of the numerically unstable region of the implicit Euler. And if that happens, then your code diverges. And so what we try to do is, so how can you, people have used all kinds of things to deal with it, right? You have local time stepping, you have multi-grid, you have continuation techniques, you have you have all kinds of techniques that people have developed over the years to try to deal with these issues. And we follow a different approach. Our main goal here is this: look, if we cannot do anything about the maximum time step that I can impose, I will change the stability boundaries of my scheme. So what we do, we call it minimal gain marching, is that we design the marching scheme and we tweak the coefficients of the marching scheme so that the region of numerical instability, here I keep losing the mouse. Where's my mouse? Oh, here. So this is the implicit Euler one is here for illustration purposes. And this is MGM. I hope I don't get sued, but this is my minimal gain marching scheme here. And this is a multi-step version of it. We can tweak the control parameter so that we can make it like half the size, half in terms of distance here along the horizontal axis, right? And now these modes that were unstable for the implicit Euler, now my stability bounds are here, so these modes become stable, right? So this is what we do. We tweak this, the stability bound, the numerical stability boundaries of the scheme, so that for the same time step, those modes that were unstable for implicit Euler become stable for this. And now they're physically unstable mode, but now they fall into the numerically stable region of the scheme, and everything converges, right? This multi-step version, you can actually prove theoretically that for infinite time steps, it converges to the under-relaxed Newton method. So the control parameter of this scheme is the same control parameter that does the under-relaxation for iterative schemes. So it's interesting. And you can see this, the bottom plot shows the line at zero frequency, right? So it is the gain along this horizontal line here, so that you can see that not only the numerical stability region decreases, so the gain gets much smaller at smaller time steps. The multi-step version has a problem though. We lose L stability. So our gain doesn't go to zero anymore. And it has also a bigger problem. As we squeeze and we decrease that region of numerical stability, the asymptotic gain goes up. So it actually tends to 1. So we lose a convergence rate if we try to stabilize the scheme, which is why we developed the multi-stage versions. We have the 2-stage and the 3-stage versions here. So they were designed in such a way that we could decrease that numerical stability region while maintaining L stability, as you can see here on these two things. So we can make that numerically unstable region as small as we want, and we can still retain the L stability, and the gain goes to 0 for large enough time steps. And this is really important because if your maximum time step is restricted, we can actually decrease that region of numerical stability so much that we can recover the quadratic convergence from Newton using these time schemes, and so we are insensitive to initial conditions and we have quadratic convergence rates, even if our time step is restricted and it has to be really small, right?
You have quadratic convergence at each time step, or you have quadratic convergence to the steady state?
Yeah, to steady state, yeah. Because quadratic convergence, you from the Newton method, you get from the implicit Euler if your time step is so large that the gain is 0.
Right, but you restrict time step.
The time step is restricted by the numerics and the physics of the problem. So what we do is we move the stability boundary to the left so much here.
But you have finite time steps, so that I don't understand how you converge quadratically to steady state.
Because we can make the gain go to 0 at that time step by moving the stability boundary to the left.
But you still have time steps. So
yes.
Your convergence will not be quadratic to steady state.
It is quadratic because the gain is close to 0. What makes the quadratic convergence of Newton is the gain going very, very small. The gain is what controls the convergence rates. If the gain is close to 1, you converge very slowly to steady state.
I understand this, but I don't understand if you have finite time step, how you converge quadratically to steady state. Even if you kind of, so anyway.
Yeah, you can see that easily in the Newton method, because when you do the Taylor series, right, you can see the quadratic term that you're knocking off there, right? But in an implicit scheme, it's the same thing. But it's controlled by the gain itself. And we do comparisons with these marching schemes, and I'll show you the CPU time comparison. So this is just to give you illustration what happens with the multi-step version of MGM. You can see the asymptotic convergence rates becoming worse because the gain becomes a lot higher, right? So this is for like a control parameter. I forgot the values, but if we keep making the region of numerical stability much smaller, you can see the problem with the multi-step version that doesn't have anymore with the multi-stage versions, right? And of course, there's a cost here because the 2-stage, I'm solving twice as many equations. In the 3-stage, I'm solving 3 equations now. So per iteration, they cost more, but the decrease in gain is so much larger that makes up for that, and you can gain in CPU time, which is what we show in the test cases. This is just some sample test cases. The Lorentz equations is an example of the multiple steady states that you have. And this plot here sort of answers that question, because depending on when we turn on, this is the initial part is an unsteady simulation. This is just a y variable for the Lorentz. Depending on where we turn on the steady state, we can converge to different ones, right? If we turn it on closer to each steady state, we converge to it. So you can see this problem has 3 different steady states, 2 non-trivial ones and 1 trivial one. If we turn it on here, we converge to this one. If we turn our steady state solver on here, it converges to the trivial one, and so on. Of course, it's a lot harder to converge to the trivial steady state because the temporal growth rate is a lot higher than the one for the oscillatory modes.
How you guarantee that you are not jumping between steady states, so that you have so what controls that you are kind of staying on the same steady state that you converge, not like your solver does not jump to another steady state in the process?
Well, if the jump occurs, I can see it, right? It starts going to one place and then switches to the other, right? But that never happens.
But you can have continuous set of steady state solutions.
Sure, yeah, you can have all kinds of complex bifurcation patterns, yeah. But I'm not moving along this is in time, right? I'm not moving along the bifurcation. I'm not varying my parameter. As I vary my control parameter of the physics, one of these 3 parameters from the Lorentz equations, then I can switch. If there is a complex bifurcation, I could move to a different one. What I'm saying is that within a given parameter set, this thing is going to be varying in time, right? Depending on when I switch in time to the steady state solver, I may converge to a different solution, depending on where in the phase portrait my solution will be, right? And then this is the interesting plot. So the black line here is the implicit Euler scheme, and you can see that as we approach that stability region, things diverge. The purple is the multi-step version, right? You can see that we can go a bit further to the left compared to the Euler, but we lose the asymptotic convergence rates. So this is the CPU time versus time step, right? So if I make the time step smaller, eventually things diverge. But if you go to the multi-stage versions, like we can decrease the stability region so much with our control parameters that we can get like super low convergence rates for time steps that are like 3 orders of magnitude smaller than you could get otherwise, right? So this is the major point for us. Same thing, this is a different test case. It's a modified Burger's equation that we use here when this thing is like globally unstable. So it's a stationary disturbance, but it grows really fast in time. You can see the temporal growth of the disturbance here. We place a disturbance in the middle of the domain, and it grows really fast in time. And then we switch, after it becomes nonlinear, we switch to the steady state solver. And then we get similar, this is quite clean, like a CPU time versus time step. Same thing, we see the implicit Euler here. For large enough time steps, we are getting the super fast convergence with very few iterations that you would get, that we also get with Newton method. This is incorrectly called Newton here, but this is actually implicit Euler, right? So for very large time steps. If we switch to the MGM multi-step, you can see again the loss of the time asymptotic convergence rates, what causes, right? And but we see that the numerical stability region is smaller because we can reach smaller time steps. But when we switch to the multi-stage version, we can see that we can push this all the way to the right. And for very small time steps, you can get the same convergence of that you get with Newton, right? And so if there was a time step restriction in this problem, we'd be able to run it with a much smaller time step and it would be no problem. Of course, this is a simple test case. This type of issue doesn't happen. The other test case we did here, this is really, we find this test case to be really interesting because we tweaked it so that disturbances of all wave numbers have the same temporal growth rate. So that we really like this test case because if there is any issue with your spatial discretization, there is exciting disturbances of any wave number, this thing will excite. So this is a way that we make sure that our spatial discretization is on point, right? Because all wave numbers are equally excited, right? And this is a plot of the unsteady simulation. We place something with a given wave number and we see it grow and propagate. But the plot looks a bit weird, right? It doesn't go all the way as we decrease the time step. We don't see that divergence thing that we're seeing before in the other test cases. And this is a very interesting phenomenon that took us a little while to understand what was going on. But so this is the unsteady simulation in blue, and then we switch to our steady state generation, right? And then the residue decays, the increment decays, but at some point, things start growing again. If you plot the solution profile, when we get to that point, what happens? As you get close to machine zero, the disturbance that had a natural wavelength oscillation to it became uniform. Once it became uniform, it starts to grow again. So what is happening? If you look at the Euler, implicit Euler stability profile, if you are at a given time step, like this solid circles, the filled circles here, once you reach machine zero and the disturbances get uniform, the frequency, this is a non-dispersive wave, so the frequency also goes to zero. So what happens if you look at the stability plot, you're looking at an oscillatory disturbance that eventually became stationary. But because we are outside of in the range of numerical stability, it still converges to steady state. But if we decrease the time step too much, from an oscillatory point of view, it's still numerically stable. But once we reach machine zero, it becomes uniform and stationary. It drops into the numerically unstable region of the scheme and it diverges. So that's why the curve doesn't go up all the way. So we find it's a quite interesting test case for the code, but it works well. We're still working on this. This is recently developed in the group. So we're trying to do tests on like 2D and 3D flows now. And there's another developmental stage for this, which is we want to do a strong stability preserving multi-stage MGM scheme so that we can go to steady state that is shock capturing. Because the problem with SSP for shock capturing is it restricts the time step, right? In order for you to have the nonlinear, to maintain the nonlinear stability properties to do high order in time. And that's a problem, right? Because we needed large time steps to get to steady state in a linear sense. So how can we eliminate the time step restriction from SSP schemes? It turns out there is a scheme that does that nobody uses. It's called diagonally split Runge-Kutta schemes. And the reason why nobody uses it is because people designed this and so that they could eliminate the time step restriction from SSP. But the problem is that when the time step becomes too large, it falls back to first order in time. So of course, nobody uses that because the point of SSP is to do high order in time. So this thing was forgotten. But for us, it's perfect because we are looking for steady state. So we don't need to be high order in time. First order in time is good for us. So we can try to tweak that method to become an MGM scheme so that we can do shock capturing and steady state generation at the same time. And so this is ideas that are under work in the group. And finally, this is the headache of my life for the past like 3 years. When lambda is equal to 0, right? The convective instability to stationary disturbances. And so I'm going to give you some background to explain that when we started this project, we didn't really understand why people had so much difficulty with this, right? So this is examples for the simulation for high fire 5 and 5B. So people are trying, this is heat flux and Stanton number on these two plots. And what you see here, what you see, you're trying to do, this is a paper from Candler's group, different types of meshes, second order scheme, first order scheme, no matter what they did, they cannot grid converge this base flow, right? The thing never grid converges. This is a similar, this is essentially an elliptic cone, right? You're trying to convert the Stanton number, different types of meshes, the thing doesn't converge, right? And there's, I really like this sentence from, this is from Kimmel's group. He actually says that it may not be possible to get a laminar base flow for this problem. And so people couldn't grid converge this. Every time they grid converged it, the solution would be different, right? And they didn't know if this is a stability issue, if this what is preventing people from grid converging these base flows. So we started looking into this, and we came up with a diagnosis for the problem. So what happens is, if you have like a convective instability to stationary disturbances, so the flow is physically unstable, has a convective instability that is physical to stationary modes. So this is all physical, right? So what happens there? Any steady excitation will eventually trigger something that for a time marching scheme, it is a zero frequency because it's a stationary disturbance, so it doesn't oscillate in time, and it's convective. So the temporal growth rate for very large times is 0, right? So, but it's a convective instability. It's allowed to grow in space, right? So if you have any steady source of excitation, that disturbance will grow downstream from that source and will increase in amplitude in space, which is what convective instabilities do. And then they distort the mean flow and they cause all kinds of things. But the problem is, okay, usually people don't worry about convective instabilities because they're oscillatory, right? If you're not putting an oscillation in there, you're not going to trigger it. But this one is a stationary. So if you have a steady excitation source, it will trigger that instability. And what are steady excitation sources? Everything is, right? If you have a non-uniform spatial distribution of your error, that is if your error does some bump in it because of your mesh, because of your flux limiter, because of whatever, that will trigger the instability at that location, right? And then you have a numerical excitation of a physical instability. And that's why you can't grid converge these things to steady state, because every time you refine your mesh, your excitation amplitude and location change. So you have the instability growing from a different place, and they grow in amplitude in space, and they deform the mean flow in a different way. That's why people can't grid converge these things. And so to the point that this is a clever way around that Kendler's group was able to do, is that they were able to tweak their meshes to put the excitation sources where they were seeing those structures in the experiments. So they could try to mimic with the DNS what they were seeing in the experiments. But this is a problem. We can't deal with it. And this is a zero. And what is the problem with having a 0 lambda, right? 0 frequency, 0 temporal growth rate. If you go back to the implicit Euler scheme, I'll go back to this later. So, okay, this is a hypothesis, right? This is what we think is going on. So we decided to test this. We go back to our favorite test case, which is that Berger problem modified so that we can have a convective instability. So this is the transition to absolute instability in this problem, this transition to convective instability in terms of the critical control parameter. So if you're in between these 2 points, you have convective instability, and you can see that the dominant mode is stationary. So the stationary mode will control the convective instability that will grow in space, right? And so this is just an illustration. My initial condition for all these 4 plots that you're seeing here is the steady state solution itself, right? So the top 2 and the one on the bottom right, this is fourth order central difference schemes. And then I do, but of course, near the inlet, I have to do biasing of the scheme near the inlet. The bias of the scheme changes the truncation error. It causes fluctuations in your spatial error distribution. even if I'm starting the simulation with the steady state, right? And this oscillation in truncation error causes an excitation, a steady excitation of my solution. It grows. I put a buffer at the inlet, which is this one, doesn't help. I put a buffer at the outlet just because I didn't know what else to do. I tried that too, doesn't happen, doesn't help. Oh, actually, sorry, this case, I actually put periodic boundary conditions with a buffer at the outlet that forced the solution to go back to the inlet that I wanted. Also didn't help. And I switched it to second order. It stays there because there's no biasing of the scheme at the inlet if you have a second order central differences, right? But then this is the most amazing thing. So what did I do there? Why is it growing? My initial condition is not the steady state anymore. It's a steady state with a little bump in the middle. An error in the initial condition was causing an excitation that remained there, that became self-sustained. And the excitation start converging from there. So I go back and forth so the simulations can start and you can see all these issues. If you look into this bottom right plot, you can see some very thin lines here. These are the two excitations that I put in my initial condition. And this becomes an error in the initial condition becomes self-sustained, even though it's a second order scheme, right? So this is the problem that stationary instability is a hell to deal with. This thing is like because what happens there? I have an initial error in my initial condition, right? So there's an error in the residue, but that error stays there for the next iteration, it becomes, even though it's in the initial condition, it becomes self-sustained, right? And so our approach is so, okay, this provides confirmation of what we were saying before about the sources of these things. So we started assuming that, okay, let's say this is inevitable. It's going to come a point that we can't prevent the numerical excitation of these disturbances. So what do? We need to kill them. We need to be able to kill them once they come up. So how do we do that? Actually, you can't. All the steady state solvers in the literature suffer from the same problem, right? Lacks equivalence theorem, right? In order for you to get a converged solution from your solver must be consistent and stable, right? Consistency, it's what guarantees the existence of the steady state. It's what makes when your solution becomes time invariant, that consistency makes the time derivative go to zero, right? But enforcing that forces your gain to be 1 at the origin of this plot.
Just one, this is sufficient condition, not
necessary. On a linear basis, yeah. On a linear basis, because but everything is nonlinear, so we don't know what happens in the nonlinear. Yes, this is on a. It was a longer text that had that, but I had to cut it short to fit in here, so the linear part went away. But you're correct. Yeah. So what is the big problem? At the origin, the gain has to be 1 for consistency. So what happens if lambda is 0? It doesn't matter what time step you use. You can never move that mode away from the origin, and the gain will always be 1 there. So every single steady state solver has this, and that's why none of them can kill that convective instability to stationary disturbances, right? It always stays there. So the numerics cannot get rid of that. So we developed a different approach to it. We call it a frequency displacement procedure. So what do? We introduce a source term that looks like this. It took us a while, but we figured that thing out. And we can actually theoretically show that doing that will move the the 0 lambda mode away from 0 if we do that. The proof is not here, but you can trust me. When the paper comes out, you'll see it. When we do that, what does this thing do? It moves that mode away from it. We have to do it in this way, U minus US, because we want to change the disturbance behavior without changing the steady state itself. So it's the same steady state, but on a different unsteady behavior, right? So that we can make the disturbance on the new governing equation unsteady. And if the disturbance is now oscillating, all the steady state solvers can kill it, right? So that's why we call frequency displacement, right? We make it not be stationary anymore, be oscillatory. But of course, I mean, what's the point of this? I don't know what the steady state is. I'm doing this to be able to find it. So I need to get rid of this guy. So
that is super similar to the selective frequency damping, no?
It doesn't have an integral in time. Yeah. I'm almost done. Yeah. So the selective frequency damping, yeah, doesn't have the integration in time. It's just that difference, right? And they estimate this by filtering the solution. So the US, they use a U bar here, which is a solution that is filtered, but the source term itself is not a filter. You know, that's the difference between the two. And so that we use some clever Taylor series expansion to replace this guy by something like this, in which the steady state no longer appears. So now we don't need to know it a priori, right? And yeah, I'm sorry for the plots. They look good in my Mac, but in Windows, they screwed it up. But this is spatial growth rate on the vertical and wave number or frequency. Yeah, it's gone. But on the left, right? On the horizontal axis. And you can see, yeah, there's supposed to be a legend here that says that when the control parameter of my scheme, which is this capital omega here, is 0, I go back to the original mode that you saw in the previous plot as the stationary dominant convective instability. When you turn on that omega, we split the curve in this way. And you see that the mode with 0 wave number, which also has 0 frequency, is now stable. So this thing converges. So there's the effect of that source term on this stability. Knowing the steady state a priori, this is not with the approximation in it, but it's just to show what happens. And I have a little plot here to show you. Now we can control the growth of that thing. So that source term doesn't allow, when we start the simulation, the source term prevents that thing from growing in space, right? So we can do this. We can prevent those disturbances from growing. And I have some more. Okay. And this is just another plot, the effect of that capital omega term. If I turn it off, what happens? This is the disturbance. I'm plotting the disturbance here, right? So you can see the disturbance growing in space, but then I turn it on and I can control that growth, right? And we can actually show theoretically that disturbance is going to be proportional to epsilon is the magnitude of the initial disturbance. It's sort of a measurement of how far you are from the steady state, and the time step and that omega parameter. So the thing is that if your solution, your initial solution is too far from the steady state, then I can make that capital omega larger and I can control it. But it turns out that it's not that easy. If epsilon is too large, if I'm too far from the steady state, this thing I cannot bring it back. And if I do my solver, the fake one, knowing what the steady state is, I can kill everything. So that this source term does work. This is the correct form that the source term needs to have. So the key is, how do I approximate this to eliminate the steady state from this? So what we are trying to do now is come up with better approximations for this thing, so that we can try to be able to damp this when my initial conditions are too far from the correct steady state. And this is at the stage we are now. Of course, this is all like a simple thing, but this is what us academics do, especially when we don't have big computers at our disposal all the time. But we did. Pedro tells me that if I don't have a 3D simulation, nobody pays attention to what I'm saying. So I brought in like some simulations of Gortler vortices. This is a difficult problem to handle because stationary disturbances, convective especially, they're usually three-dimensional. You never find like a simple model problems that will have those stationary disturbances. So to be physical, you need to go to 3D. And in order to do the 2D and the 1D case, we have to tweak the governing equations, right? But we eventually went all the way down to that. And what you're seeing here is a Gortler. We have the leading edge here. So we have the, let me do this for the audience here too. So where's my mouse? Okay. So we have the leading edge here. So we have the leading edge shock. You have a suction and blowing at this strip. And that excites the Gortler vortices. In the beginning, this is not turned on, and then we turn it on, and you can see this is the streamwise velocity isocontours in this plane. And we're also plotting the streamwise disturbance isocontours here, so that you can see the development of the Gortler vortices in there, right? This is a basic simulation, nothing different here. So just to show the Gortler vortices are convective instability and are stationary. So this is a physical test case. So what happens when we do our procedure in it? If that excitation is small and we are not too far from the steady state, you see the plot on the right. We see that we eventually kill that thing and we recover the original steady state. But if our disturbance is too large, then it stays there. So we can never get it to properly converge, and the thing stays there, right? So we do need a better source term, a better approximation for that source term in order to make this thing fully converge. So this frequency displacement procedure, we are on the good path because there's no alternative. So there's nothing else in the literature that can make this thing converge. We tried selective frequency damping, Newton, boost comp. We tried all these schemes we know how to do in our group. We tried them all. None of them work when the thing is convectively unstable to stationary disturbances. So there's no alternative. This is the only one I know of so far. And we are close, but we're not there yet. But there's hope. That's what matters to keep us going back to work. So this is it. We are trying to, and there's one key thing that I didn't mention. WENO is quite nice. We're having this conversation in the morning. Those simulations that I showed you for this, right? Everything triggers this freaking thing. So when we run this simulation with WENO, we don't excite this instability, because WENO has an interesting ability to smooth out the spatial error. So we don't get those bumps in the spatial error distribution that excite that physical instability. So if we run the same problem with our WENO scheme, nothing happens. We put the steady state and the initial condition, it doesn't get excited. So one of the things that we are trying to do right now is test this. So, okay, maybe there's some hope that if we run the cone with WENO, this is some meshing that we try to do, and this is a circular cone at an angle of attack that Milan gave to us. So we are reading that. Our code is generalized coordinates, so we cannot run the cone yet, a full cone, so we cut off the nose. We read the data from Milan, and we put that in inlet condition, and we run downstream of the nose tip. And this is an example of the mesh that we use, and that's what Romulo is trying to do here with Pedro right now. And in the hopes that maybe just the pure WENO will be able to smooth out those noise sources and be able to generate a grid converge a steady state without those stationary cross-flow vortices that keep appearing for the cone, right? This is what we are trying to do. I don't know if we're going to get there. In parallel, we're trying to improve our FDP scheme to see if those disturbances get excited, we might be able to damp it. So these are the two paths we're trying to do. And that's it. Just 1 minute late. Thank you.
More questions from participate behind the corner.
Yeah.
I'm sure he has a comment about this,
But in-person audience has a preferential treatment.
So for the supersonic cylinder,
Okay.
striations, steady state what we're trying to converge. Like you mentioned that you're trying to align the grid now.
Yeah.
Have you tried like packing the grid slightly away from where the actual shock is supposed to be and see if your steady state solution is
Can we repeat the question?
Yeah, so he asked me in the cylinder if we try to change the mesh around the shock.
slightly displaced from where it's supposed to be.
Yeah. So we actually did that, but not with the cylinder, but with a blunt nose on a 2D plane. And when our mesh around the shock is not refined, we get nice convergence to steady state. If we try to refine the mesh around the shock, it doesn't converge anymore. So we see the exact question that you're raising. We are seeing that sensitivity with the blunt nose, the same thing. And so we are trying to do the alignment to see if we can get rid of that and refine the mesh around the shock and still be able to converge the residue. But yeah, what you're suggesting does happen. There's a mesh sensitivity there too. Yeah.
Do we have maybe ask if people online have questions so that then they can speak.
Yeah, sure.
Right
So yeah, if there is anyone listening to me and you want to ask questions, please go ahead. Otherwise, people here want to go eat. So.
This is going to pass off on the striation thing. We found recently that if we were using Mike Park's refined code to adapt to the mesh. Of course, they're not aligned in terms of the control volume because you have spaces crossing the shocks.
Yeah.
Well, we found that if we restricted the aspect ratio of the cells to be something 5 or less, all the striations would go away.
Hmm.
So some magic happens when you have basically isotropic cells at the shock. Don't know why yet.
That makes some sense, right? If your mesh is too like skewed, right? At least I'm thinking about the characteristic-wise WENO thing, right? He has to separate the characteristic directions, right? And if your cell is not, he'll be able to do that better in one direction than in the other. So maybe that separation is not being done properly, you know. And that's why maybe if you have like very nice cells that are close to a square as possible, he'll be able to properly do that in all directions.
It was in Kyle's hypersolve, so it was basically a finite volume scheme, alpha damping scheme.
But do you know what do they use for the inviscid fluxes to discretize them? What method?
Oh, we tried everything. We had Lax-Wondrop row, rotated Riemann row. We had all sorts of stuff in there. They all showed the problem. Until you get an aspect ratio of less than 5, and magically it's clean.
For all of them? For all the classes?
Yeah.
But it's all flux difference splitting.
Flux, yeah. Well, Lex Friedrichs.
Lex Friedrichs is flux vector, right?
Yeah.
Okay. Yeah.
But it's a unstructured mesh. It's not a.
Ah,
sort of
okay.
triangle.
Yeah. It's trickier. Yeah. Yeah, I don't know. We want to try that with the alignment because that's what's the standard thing in the literature, right? If we can align it, and I don't know.
That's what this deformation when you have, right? So when you have curve and high aspect ratio grid together, you have what we call grid deformation problem. So basically, you do not reconstruct. You overshoot when you reconstruct kind of to long sides of your cell. So restricting aspect ratio is one way to do it. Another is like what we said, like we use what we call approximate mapping, but you need to know what to map about. We typically map about the surface, but now you probably need to map about expected shape of the shock.
I've seen in the high-speed aerodynamics portfolio from the Air Force, there's a new guy working on this HP finite difference methods, but he's doing it in a different way, where he shapes his volumes in his finite element so that they can conform to the shock. So he makes the cell adapt to the shock at the shock, and he's been able to get.
This refine adapt cell.
Yeah.
You're talking about where you actually have it in the equations.
Exactly. So there's an optimization procedure that does that automatically within the solver to adapt the mesh to the shock, and he can get very clean solutions. I don't know how costly that thing is, but yeah.
But the DE elements so that super clean was not viscous, was in Diskin. And we were trying to do it with the project for viscous, and that was other question.
Yeah. It was a very preliminary work. It was just his first time presenting, so we'll see what comes up next year. But yeah, I found that very interesting.
Okay, thank you, everybody. So that we are very excited. We are happy about attendance here. As our president, I'm sure he will repeat what I just said. Everybody is very welcome and invited to join
Join us for our Thanksgiving dinner.
In the food consumption.
He wrote his wife always makes sushi for Thanksgiving dinner, and so that's wonderful too. We have other things. We have had Thai and other things too. So it's potluck, but if you haven't been, come on over.
Yeah. And I brought very good sweets. Okay.
Thank you, everyone. Thank you, everyone online as well.
Everybody invited.